Hey everybody, welcome to the worksheet 21 video series of solutions. For question 1, this is probably, in my opinion, the most difficult question. We're just going to be looking at geometric isomerism, so determining if these are cis-trans isomers. So for my problem setup, I was given all hydrocarbon chains. I've seen a couple variations of this problem where there are carbon rings. So I'm going to try to discuss carbon rings after I get through this part of it, but bear with me there. So if you have all linear choices, what you want to be looking for these cis-trans isomers, you want to look for structures that have double bonds. You need to have a double bond to exhibit cis-trans isomerism. If we have a triple bond, for example, this triple bond is linear in shape. Because it's linear in shape, that means that we can't have two groups on opposite sides. Everything is going to be on the same side in this linear conformation. If we're looking at a single bond, single bonds are able to rotate, so we don't consider these to have cis-trans isomerism. That's why we're only looking for structures with double bonds, and we need to have also one more criteria once we have that double bond. So once we've identified a structure with a double bond, we want to check and make sure that there are two different groups on both sides of that double bond. What that means is we'll just draw in what we have going on here. So if we analyze this skeletal structure, we have a carbon right here attached to another carbon and then another carbon. This carbon has 3 bonds, meaning that it also is going to need a hydrogen. This carbon over here is the same, so it's also going to need a hydrogen. And then we can see that about this double bond, we have 2 different groups on each side. We have the CH3 and then we have the hydrogen, and then we have the hydrogen, and then we have the rest of our parent chain over here. So we have these 2 different groups, so this compound does exhibit cis-trans isomerism. We can come over here to B, we can draw in our hydrogen, and we can see that B also contains a double bond, and it has 2 different groups on both sides of that double bond, so this is also going to have cis-trans isomerism. A also is going to have cis-trans isomerism. It has 2 different groups on both sides of the double bond. We have a hydrogen and a methyl, and then a hydrogen and an ethyl. So we have 2 different groups on each side. So we can have cis-trans isomerism here. For D, we'll draw in our other hydrogen. And we again have 2 different groups. We have the methyl, the CH3, and the hydrogen, and then the methyl and the propyl over here. So this is also going to have cis-trans isomerism. Last up, we have E. So E, this is going to have, we need to add in our hydrogens about the double bond. We can see that we again have 2 different groups. We have the methyl and the hydrogen, and then we have the ethyl and the hydrogen. So E is also going to exhibit cis-trans isomerism. E is actually the same molecule as A. A is just the trans version, and E is the cis version. So this is further proof that both of these are cis-trans isomers. The other ones are cis-trans isomers as well. However, this question just isn't showing their counterparts. So we also are now going to take a look at ring structures, because I know I didn't get any rings, but this problem will give you ring variants. So I'm just going to come up with a basic chair conformation quick. Some of your rings are probably going to look like this. So if we have a chair conformation, what we need to have 2 unique groups. So we'll put something like a chlorine, and then we'll put something like a methyl, so just a CH3. So we need 2 unique groups on 2 unique carbons. And then each of these is also going to have a hydrogen attached to it. So this is how we're getting our 2 unique groups on 2 unique atoms. Basically what we can have happen here is within this chair structure, we can have both of the molecules on the same side. So this would be the cis conformation of the chair. And then we can also redraw this ring so that we can make it trans. Pardon my ring drawing. So we'll keep our chlorine going up. And then we're just going to draw a line where our CH3 is now going down to the bottom of the ring rather than pointing up towards the top. And then in this conformation, we still have this hydrogen that's now going to be up. Then we'd have this hydrogen that would be down. So this would be our cis conformation, and then because they're on the same side, and then now that they're on opposite sides, we're going to be in the trans conformation. So if you have a ring, just remember that you need to have two groups on two unique groups on two different carbons in order to have this cis-trans isomerism, whether it's a 5-carbon ring, 4-carbon ring, or a 6-carbon ring like I have shown here. So then to give the correct answer for this question, all we're going to do is just scroll down. So we've said that all of these 5 submit cis-trans isomerism. We can see that A, B, C, D, and E is the correct answer. You're probably going to see a lot of variation in this question. If you struggle with this one, just feel free to reach out to us. I know that I can't explain every single structure in one video, so reach out if you need help, and good luck.